Raindrops are small spherical packets of water which fall from the sky. A similar droplet will slide slowly down a window after being formed by rain, perhaps combining with other droplets along its way. What holds these droplets together? Why do droplets behave as they do when they're in contact with surfaces? A water droplet can be broken down into smaller droplets, but this proves to be increasingly difficult the smaller the droplet is. The smallest amount of water is defined as a molecule, and a droplet consists of a large number of water molecules.
A droplet of water can be viewed as a medicine dropper creates it. Water sticks to the glass dropper as the droplet is formed. After the droplet becomes a certain size, the medicine dropper no longer supports its weight and it falls. The surface upon which a water droplet is placed affects its shape and ease of movement. Water droplets behave differently upon different coatings applied to the skin. Water will run right off olive oil at a certain angle. A droplet of water placed on some non-stick cooking paper can be moved when enough of a toothpick is in contact with the droplet. The toothpick, when moved closer to a water droplet, deforms the shape of that droplet. When two droplets of water touch each other, they quickly combine, forming a larger droplet. Scotchgard can be sprayed over a single-ply tissue to make it capable of holding more water than an untreated tissue. The untreated tissue becomes wet and allows the water to pass through. Scotchgard is hydrophobic, meaning that water is not significantly attracted to it.
Two observations are made about water from these experiments. Liquid water is attracted to its own molecules, forming droplets. When this occurs, cohesive forces are said to exist. Water is also attracted to other substances, such as the glass dropper and the toothpick. When water is attracted to other substances, adhesive forces exist, which are said to wet other substances.
The combined effect of adhesive and cohesive forces in water will cause paintbrush bristles to draw together and makes it difficult to pull wet microscope slides apart.
A water droplet, in free fall, in the absence of air, is free of adhesive forces, and its shape totally depends on cohesive forces. The cohesive forces of molecules on the surface of the water droplet are attracted to each other and towards the molecules within the centre of the droplet. The overall attraction of molecules on the surface of the water towards the centre of the water acts to create the smallest surface area for the droplet of water, which is a sphere. This effect is known as surface tension. Surface tension can be demonstrated by adding paper clips to a glass of water until it overflows.
The cohesive force of each molecule on the surface acts towards the centre of the water. It is possible to see the water over the top of the glass. The water volume above the top of the glass gets bigger until the pressure from the weight of water forces some of the water over the edge of the glass. Needles or razor blades can be floated on the top of the water even though they are denser than water and normally sink. The tension produced by the surface of the water holds this surface together, opposing the force of the weight of the needle or razor blade, and consequently it floats. A lid with holes in it will also float. If there is enough water above the lid to wet enough of the lid will take on water and sink. The weight of these objects have the effect of distorting the shape of the water surface. A special floater device can be created which will demonstrate the cohesion of the surface from within the water body. The floater will remain under the surface of the water once pushed down, although the surface of the water will be distorted. The device requires the appropriate weight to counteract the effects of cork's buoyancy, otherwise the device rises too fast and easily breaks the surface tension. Detergents increase the wetness of water, meaning that the cohesive force of water and surface tension decreases. Water droplets are easily added to a 5-cent piece, but when detergent is mixed with the water, not as many can be placed before the water spills. String cut into small pieces will initially float without breaking the surface of the water. Detergents increase the wetness of water, allowing the string to become waterlogged and sink quickly. Eventually, the string floating in plain water will take up enough water and sink anyway. Detergent can also be used with water to create films of liquid in loops of wire such as those used for blowing bubbles. A loop of thread is placed inside a wire loop and the film is broken with a piece of paper. Both surfaces of the film pull at the thread to create the smallest surface area quite rapidly.
A device for measuring the surface tension of a thin film could be constructed that would apply a force equal to that of the force which is applied by the film. Such a device would need to overcome the effects of friction in the mechanics of that device.
Floating toothpicks are repelled by soap. The surface tension on the soapy patch of the water surface is less than the surface tension on water where the toothpick is floating, and the soapy water surface spreads out, whilst the unaffected water surface tightens and drags the toothpick along with it. Talcum powder or black pepper applied such that the particles are clumped together is cracked by this effect of soap. A loop of thread floating on the surface of water will jerk when soap is added, depending on the position of the soap and the curvature of the thread. This surface tension localization effect is demonstrated dramatically using a floating razor blade or bread tags and some detergent. Whilst soap and detergents repel, it is possible to attract a toothpick by using sugar cubes, because sugar cubes draw water upwards. A cork floats to the outside of a glass of water and stays there because water molecules are attracted to cork as well as to the side of the glass. Water moves up the side of the cork and surface tension pulls the water surface and cork to create the smallest area on the side of the glass closest to the cork. If you fill the glass up so that the water no longer has attraction to glass sides, the cork will float about in the water. Water is drawn up a small capillary tube because of its attraction to the sides, forming a meniscus, meaning the curved surface within the tube. A pin between two microscope slides wrapped in a rubber band demonstrates the strength of capillary action at increased spacing in between the slides.
The shape of the meniscus is determined by the amount of attraction to the side of the tube and the surface tension of the liquid. The smallest capillary tube that I have is made from a different material than the other tubes.
Different materials, as capillary tubes, have the effect of drawing different amounts of water. The smallest capillary tube doesn't draw as much water as if it was made from the same material as the others.
Liquids other than water will be drawn to different heights depending on the adhesive and cohesive properties of that liquid and how close together the sides of the capillary tube are. Mercury actually descends in glass capillary tubes, forming a convex meniscus. Capillary action also is demonstrated using blotting paper. Adhesive forces attract the liquid, and cohesive forces continually draw water from the surface.
It takes different liquids, different amounts of time, to travel up a piece of blotting paper, and consequently a mixture containing different liquids could be separated in this manner. This is known as paper chromatography. Capillary action is used in candles and in kerosene or alcohol burners, where the time taken to draw up the liquid and the wick's size determines the flame size and how much heat is given off.
Whether there is a droplet or contained within a large container, water has attractive forces that cause it to act predictably with other matter and governs the shape of water droplets. The tension on the surface of water allows other bodies to be moved with a change in that tension. Water's own movement depends on the attractiveness of other bodies, such as in capillary action. Other liquids exhibit the properties that have been described, but none of these liquids is as abundant as water is on Earth.